Hello, my name is Grebennikov Roman, and I will tell you a couple of horror stories about memory usage of Scala programs, and particularly about case classes. A short note about me, that's my face. I work at a company called Findify, and we do search and recommendations for e-commerce. And the major part of this talk is about the problems we encountered with doing recommendations and search. But as for the recommendations, the problem is that we need to do this for a large scale, for a large number of merchants. There are 1 million users coming, and these recommendations are not static, but they are personalized and changing depending on the customer browsing the website. And to do this, you need to keep a lot of data about user behavior in memory. And this thing can be really a problem, because if you have only, I don't know, 1,000 parallel users doing some things on a merchant website, that's fine. But if you go to the 1 million users, it can be tricky. Because to store a lot of user behavioral data in memory, you need to go to the playground with a large JVM heaps. And if you have a large JVM heap, you start playing the game with a garbage collector, and most probably you will lose. So it's a trade-off between the application throughput and latency. You can get some latency spikes. You can get, and having a lot of data in RAM is just costly. You need a lot of hardware to host your application. And but the story usually starts from modeling your domain with the case classes, if you're using Scala for that. So let's imagine we have a case class called PAGEVIEW. It has only 2 fields, like the identifier of something and the timestamp. And here comes a short quiz. So we have a PAGEVIEW instance like this, so it has only 2 fields. And how much heap space does this PAGEVIEW use? But there are some options. But before voting, I will just give you some hints. So you know that if it's a if it's a case class, it's still a JVM object. It has a header. So header is usually about 12 bytes. We have like 4 to 8 bytes for the string. We have 8 bytes for the long value. So maybe it's 24 bytes. Who's voting for 24? Ah, suspicious. OK, but the string itself is also an object, so we need to store a reference to the string, which can be from 4 to 8 bytes. The string itself is an object. It has a header. It has some data inside, so maybe it's about 48 bytes. Who's voting for 48? There's a trick, you know. But the string itself has an array of characters, and array itself is also an object. We need to store a reference to this thing. We need to store the length and the bytes itself, so maybe it's 72 bytes. Who's voting for finally 72? Ah, me also. But we forgot about object padding, because if the object is not aligned in RAM, the hotspot might inject some free space at the end of the object, so it will be like 24 bytes or 32 bytes or so on. So maybe it's 96. Ah, the pessimists. The correct answer is about 72, because we are lucky enough to fit into the object alignment with this object. But it can be 96 if we are not lucky. So for that, why it happens, we will use a tool called Java Object Layout, and we'll see what's really what's happening inside of our case class. No, not this one. So Java Object Layout has an SBT plugin, so you can just plug it into your SBT and use it like this. Jol internals PAGEVIEW, and it will compile something. We need to wait a bit. But then it will dump a lot of stuff on our screen. But the most important thing is that we still have here this 12 bytes object header, the reference to the string, and the 8 bytes for the timestamp. It's perfectly aligned to the 24 bytes. For the string itself, it will be a bit different. And it's 12 bytes for the object header. We have a reference to the character array, which is 4 bytes. We have a hash code for the string itself here. And we have this 4-byte loss due to the alignment. It's for the Java JVM 8. For the JVM 9, it will be a bit different, but it will be still 24 bytes for this case. And I have no idea how to dump the internals for the array of characters in Java Object Layout, but you have to believe me that it's the same story, the header length and the bytes itself. So if we draw it all, dump it all to the diagram, you'll see that our simple case class actually is a very complex structure. So there is headers, references to other objects, header, hash codes, alignments, and length, and so on. So actually our data from the case class is with this time stuff and these characters. And all that structures are just hidden for us from the Java virtual machine. And if we sum it all together, we'll get quite a huge overhead. It depends, but I've seen numbers between 60 to 90% of the overhead if you're using case classes or just regular classes. It doesn't really matter for storing a lot of data in the heap. And it's very disappointing for me because if your application is memory intensive and you're paying for this overhead with your money, but you're not really using this memory, just paying for nothing. If you go to the collections, you see that if you use a list, it's a very simplified definition of a Scala list. So it's still a case class. It has a reference to the head. It has a reference to another wrapper of the value to the tail. And it still has an object header and so on. So if you, again, dump it to the diagram, you see it's a very complex structure of objects referencing each other. And these objects are just distributed almost randomly into the heap, so it's not really performant and not really effective from the memory usage perspective. So just for a more precise use case, so let's have 1 million of page views in a list, and we'll use another tool called JAM. It's a Java agent for memory measurements. It's a Java agent. You can and it has a simple API, so you can put a reference to some object. It doesn't really matter to which. And it will traverse all the references coming from this object and compute the memory usage of the whole tree. So it is not super precise, but it's giving an approximate measure of the memory used by your data structure. So if we plug it to the JAM, we'll see, so for the 1 million of page views in a list, so it's a graph showing number of bytes used by the element, depending on the number of elements. So you see it converges somewhere on the 96 bytes per element. So you see it's just a lot of memory. It's not just because of the Scala collections implemented this way. It's just a problem of it's not a problem, it's a feature of the Java virtual machine. If you do it the same thing, but with the primitives, you see the same situation. So it's just a list, set, and vector of integers. So for a list of integers, you have 40 bytes per 4-byte integer overhead. It's 90%. For vector, it's a bit better. For set, it's a bit worse. This madness happens for different reasons. I can explain it later if anyone is interested. It's a problem of the virtual machine itself. It's a trade-off between the managed runtime, for a managed runtime, between the performance and manageability and so on. So then let's have just a short journey to the non-managed world and write some C++ for that. So we have just a class called PageView with the same fields as it was for case class in Scala. It's not very correct way of measuring the memory usage for the PageView here, because it will measure only the stack portion of the PageView itself. But anyway, if you draw it in a diagram, how it will be distributed in RAM, so you see that the length of our string is right inside of our page view. There is a pointer to the bytes, no headers, and just time, and that's all. If you see how it will be distributed for just a vector of page views, all the page views will be just in a single chunk of RAM, one after another. There might be some padding between the objects, but at least it's controllable by the compiler. You can just, it's up to you. And it's much more, it has much better CPU cache usage, so your processor doesn't need to traverse this weird data structures of objects referencing each other. And it has almost no RAM overhead, just a single reference for the string. So that's much better. And the question is, can it be achieved within the JVM? And in the perfect world, can it be achieved with Scala? because we're on a Scala conference. And the answer is yes, but there are multiple projects doing similar things, but all of them has some problems with this. So the first one is Project Valhalla. It's an experimental project to have value classes on top of the GVM. As far as I remember, it's not planned to be released on Java 10, so it's maybe for a future release. I don't know well when it will be available. The Chronicle map is very Java-specific. It has a complex API. It requires a ton of boilerplates. So if you have a case class, very rich case class structure, you need to somehow serialize it and deserialize it. And for MapDB, it's also map-centric, focused on mostly on the persistence. It doesn't work with Scala for some reason because of some weird Kotlin compiler bug. So if you try to use MapDB from Scala, you'll see that it won't compile for some reason. The Scala of heap is dead, but it was very promising a couple of years ago. And the Google Flood buffers is a code generation and a completely different API. But it's solving the problem, but you need to rewrite half of your application to use it. And that's also very disappointing. So we decided that what if there will be a library that it will behave like a Scala collection, or it will be just an extension for Scala collections, and it won't require any boilerplate, so it can encode and decode your case classes structures just transparently to you, and it's going to have overhead because of this encoding and decoding, but the overhead shouldn't be really huge. So we decided to just implement it. So that's, I'm introducing to you the scala-packed library, which is actually an extension for a Scala collection, but it's baked by the array of bytes. And let's just have a short try of that library. So let's have just a list of page views, like this. Page view, it has simple ID and simple timestamp and to list. Yes, so it's just a page view. I have a function which actually calls this gem tool to measure the memory usage of this list. Just a two-line function, but it's 96 bytes per page view, so it's quite a lot. And we can have a packed list thing. So it looks the same, but the type definition is a bit different. But the memory usage is much better now. So it's almost 4 times less. So it was 96, now it's 25, which is quite a good thing. It can be done the same way for the maps. I can show you, but as far as I remember, we have not that much time. So lists and maps, and in future maybe sets, can be implemented this way. It feels like magic, so it was just Scala collections, but it was 4 times better memory usage, but it's not. And so I will tell you a bit a short story. You have a question?
Yes. Does this also support things like builders, buffers, that sort of thing? Because here you took a big list and packed it. It would be nice to build a packed list to begin with.
Yes, there is a builder for the Scala. So like the scan build from macro and builder, they're available for these classes. So you can use it manually without this too magic. So for the serialization, it works as most of the serialization formats. So you have some type classes for basic types like integers, strings, and so on. And when you have a case class, you just use a bit of Shapeless to derive the type class for this H list. So Shapeless is everywhere. So for just our page view case class, we have 2 fields. We can have a generic representation of this case class as like just H list of string and long. We just traverse this H list and derive the type class for that. But technically, there are some, so for this simple case, it looks like what can go wrong, but there are different levels of madness when you're trying to derive the type classes, because there are, so the first level is like the page view. You have only fields that you already have type classes for, you derive, that's not a big deal. That can be a bit more harder when you have another case class, but you don't have type class for that, so you need to derive for that one and then for the regular one. It can be recursive. It's also possible, but it also requires some code to be written. And then you have the ADTs, and when you need to derive a type class for the nightmare thing, or just the random combinations of all of these four. For me, when I tried to do it, I was not really comfortable writing shapeless code, but surprisingly, I found an interesting thing that it's a kind of a helper thing. OK, so this collection of helpers for the label type class, just type class, and so on. So, but the general idea of this family of the helpers is that you just define a couple of type classes for like hnil, for hlist, and if you want it to work with the coproducts and seal traits, it's just the same for cnil and clist, and it will just work without much of the code written for that. So I will just show you a short demo about how it looks like, because I was very surprised that how can it look like. For a regular one, for the type classes, it's a regular type class for show. So it's a value of type t, and we should dump the string here. Let's have a type class for string show. We can write it like a new show of string, and here is def print, but we can simplify it in a really interesting way. Just not a new one, but just a show, and
that's only in 212, though, right?
Yes, it also works on a 212, but still it can be done this way. So the same thing for the long show. It's show long. It's to string. So it's a single method something. I don't remember the correct name. So we have some basic type classes, and then we need to derive something for our page view. So let's have an object called magic, which extends the product plus companion for the type class of show, and object type class, which extends this labeled product type class for show, and it will ask us to implement a couple of methods. The first one is this empty product, and for our case, for our type, it will be just empty string. And the one for the hlist, the definition is quite long, so I will just cut it into pieces. So we have our value, and we have type classes for head and tail, so we can just use them as type class for head, print the head, and type class for tail, print the tail. And the final one is the projection. So you need to have a type class for f, when you have a type class for g, and you have this nifty functions to convert from one to each other. It will be instance to value, like this. No, maybe from.
I think you just forgot the dot print.
So yes, you're right. Thank you. That happens on the live coding. So that's all what we need to do to derive this. And we'll have also a function to derive our type class for the type T. We'll have an implicit there. Show show T, and it will like this. And the final bit of magic, not really a magic, importing our construct we did. And then we can try to derive the type class for our page view like this. So show will be derive show for page view. And let's hope it will compile. Always scary. Oh, it works. Now we'll try to use it like page view show print page view full one. And let's run it and see what will happen next. Yes, it works as it was intended to work. So it looks pretty readable, even for the person who never seen Shapeless but knows something about H-lists. And if you switch from labeled, not product, but labeled type class companion, so it will require you to do the same, but for the co-products. But it will look mostly the same, and it will work well. So that's how we use it for the derivation of encoders. Yes, we can use some Creo or something, but it's always useful to make your hands dirty with this. For integrating with the Scala collections, it's always it's like a moving target, so it works with 2.12. The integration, as it's written now for scala-packed, won't work with 2.13 because of the Scala collection Strawman project, which is breaking everything. But to integrate with Scala collections, you actually need to do this builder for this packed list, packed map, and packed anything. And the implicit, the type class to plug your collection implementations to the Scala collection hierarchy. So that's all, and it's covered with a bit of pain, but it works quite well for us. So for the list of a packed list is just a huge chunk of bytes, which is and when you create a list, you just dump the page view data there, and it just serializes it one by one. The buffer is expanded, and you are not really limited to the case classes when you're putting something there. You can use a list of integers, and it will serialize to the 4-byte integers, and having no overhead, at least for the memory usage. It will have other overhead because of the boxing, but at least the memory usage will be fine. So in a structure as it's distributed on the memory, it's just, you see that there is no object headers, there is no references, everything is just packed as hard as it can be packed together. So, and if you are just iterating over that, you have size of the object, so you just go from one to another, and not a big deal. So we can use it the same thing for but for the integers. So 0 to 1,000 to list. So int list. So you see it's 40 bytes per integer, which is a lot. We can do this a bit of magic with the there are different representations on the byte array, but now it's only 4 bytes per integer, which is quite well, and it is actually expected. If you compare this implementation with the collections intended with no boxing, and mostly for the collections of the primitive values like the box and all that stuff around there, our implementations still have some problems of the Scala collections of the boxing itself. So it cannot escape it, so there will be a performance penalty if you're just using the packed list as a list of integers. The memory usage will be fine, but the overhead of the boxing and unboxing is inevitable in this approach. So for the maps, it's implemented in a bit different ways, not as a Scala collections. So it's an open addressing hash map. There is a table of the buckets with an offsets to the buffer. So when you put an element to the map, you just find the the first free space on the buffer, get this offset. This offset is just the object offset. You compute the hash code and put it to this bucket table, and then write the offset to the bucket table. So it's just an open addressing hash map. You can Google for it how it works. And all these collections still have some limitations, a lot of them, but they are working somehow. So the first problem is that they are mostly immutable, because if you are going to, so you have a finalized map, and you are going to change the element inside of this map, it will be really problematic, because if the element you are going to change, like this one, if it fits to the space, that's possible. But what if it doesn't fit? So you somehow need to mark the space as free and then to inject it somewhere at the end, and most probably then you need to collect some free space and do a garbage collection there. So we decided not to do it. So it's currently just completely immutable, and if you decide to inject something there, it will rebuild the whole collection. So it's better not to use it as a mutable collection. Just build it and use. The performance semantics is a bit different, because this list, for the Scala list, it's just a linked list. You can easily prepend element there. So the operation of prepending element to a list is almost free, because it's just a linked list. For the packed list, you cannot prepend something at the beginning of the array of bytes. You need to do either relocation or do some smart tricks with multiple pages of the data and relocating the single page and so on, but it's not yet implemented. But still, it can hurt you if you're using it as just a regular list. And not all Scala collections methods are optimized for the layout we use. So for example, the length of the list, for the regular list, it's just traversing the linked list. For the packed list, it's not deserializing the whole data. It has the object size encoded right into the byte array representation, so just skipping all the objects. It's still traversing, but it's not unpacking them. But not all the methods are that smart, so some of them and most of them will cause the object unpacking, so it can be quite slow. And the boxing. Boxing is everywhere, but that's a problem of the Scala collections, not of the scala-packed library. So for the benchmarks, it looks like this. So it's list of integers, and you see that the packed list for the memory usage is performing quite well. This madness at the beginning happens for multiple reasons. So for set, because in Scala collections there are specific instances for set for 1, 2, 3, and possibly maybe 4 elements. And then it goes to the regular implementation. For the vector and packed list, there are some buffer prelocations at the beginning. So if you have only one small integer and 100 bytes buffer, the memory overhead per element will be quite huge. But that's the problem of the implementation of this. So you shouldn't really use it for collections of 1, 2, 3, and 10 elements. For the list of PAGEVIEW of the memory usage is still performing quite well. The same issues at the beginning, but that's expected, and it still uses much less memory than the regular Scala collections. And the most important thing is just the performance. So I've did a couple of benchmarks for the list of PAGEVIEWs. So it's a filter benchmark and for each benchmark. Filter is rebuilding the collection while iterating according to the function you put it there. For each is not rebuilding a collection, just iterating over it. So you see that vector and list have different performance characteristics, but compared to them, the packed list is always slower. But the interesting point is that it's not that much slower. So it's maybe 20% slower than the vector and 2 times slower than the list. For each, without the rebuilding of the collection itself, it's still slower, because when you do a for each, you need to unpack all the elements in the list. So for list, you just have an object function, you apply the function and iterate. Further, for packed list, before that, you need to unpack this object. For a map, it's also 3 benchmarks. The first one is the building of the map. It's also slower because compared to the regular map, you need to serialize all the objects to the byte array. And for the lookups, the lookup is also slower because of the you need to deserialize this object. But the interesting point with looking up non-existing element is faster. It's just because of the underlying data structure is different. So packed map is an open addressing hash map. The regular map is like a tree-like structure in map. So that's why the performance characteristics are a bit different. So for our using this library in production, being honest, not yet. So because there are some issues with this, mostly when you use very large collections of elements, and we still don't, and the performance characteristics are not that good, but we're working on it. There are some bugs, most probably, but you might hit them, but pull requests are welcome. And it was my personal first deep encounter with Shapeless, and I've really learned a lot. And so it's not that scary, actually. So I recommend it to anyone to extend your understanding of the Scala type system. And there are some. So the scala-packed project is on GitHub. It's on Maven Central, so you can just plug and play with it. Java Object Layout and Gem are also available. The JOL is just part of the OpenJDK. Gem is also on GitHub on Maven Central, so we can freely use it. And that's all. If you have questions, you're welcome.